Okay guys, so let's talk about math, polynomial functions, which is the first unit of grade 12 advanced functions. Here we have a graph. How can you tell if it's a polynomial function? So all polynomial functions come with a set of characteristics, but when graphing, the most common way to see if it is a function is the vertical line test. You basically just draw a line down the graph. If more than one point on the graph intersects with the point on the vertical line, it is not a function. So on this graph over here, if we were to draw a line down any point, only one point intersects. So this graph would be a function. Another thing you can pull from a graph is whether the x is continuous or not. Since a polynomial function has no restrictions on the x can basically be any values. So if x is continuous, we know that it is a polynomial function. If x is not continuous, we know that it is not. On an equation, doing a vertical line test is a little harder to do. So there's a set of characteristics that can help distinguish whether it's a polynomial function or not. For one, all exponents must be positive, and all exponents must be whole numbers with a consistent variable. No variables should be in the denominator, there should be no square roots in the equation, and there should be no trig. So this equation over here, it follows all the criteria. It has positive exponents, it has whole numbers, consistent variables, no variables in the denominator, no square root in the equation, and no trig. So it is a polynomial function. But this equation over here follows most of them besides no trig. So you know that this is not a polynomial function. Since we're already on the topic of characteristics, let's also discuss finite differences. Finite differences help us evaluate the value of the highest exponent, which helps us understand the shape of the graph. A polynomial function to the 9th degree will have a constant of the 9th difference. So, if a function is constant at the 4th difference, it is a quartic function. If it is constant at the 3rd difference, it's a cubic function. You find these differences by basically subtracting the y values going from bottom to top. So over here you would subtract b to e, e to c, c to d, until you find a constant number until you find a constant difference. Also, another thing to keep in mind, if the constant difference is a negative, the coefficient value for the very first and highest exponent will also be a negative. Okay guys, so now we're ready for some questions. So the first set of questions I have for you is this. Are the following polynomial functions, and how do you know? So A is a graph and B is an equation that says y is equal to 4x cubed minus 3z squared minus 2x plus 4. So A and B are both not polynomial functions. A passes the vertical line test, but it does have a restriction as the graph is not continuous. So you know that x cannot be any value, therefore it's not a polynomial function. B has two sets of variables in the equation, so that can also prove that it is not a polynomial function, as polynomial functions must have consistent variables. As you can see over here, there's the y is equal to x, and then there's a z over there. So you know that it is not a polynomial function because it has two sets of variables in the equation. Okay, so my other question involves finite differences, which helps us evaluate the value of the highest exponent. So keeping in mind that a polynomial to the nth degree will have a constant of the nth difference, let's try to figure this out. So my first question is a linear function. So a linear function will always have a constant first difference. So which one over here has a constant first difference? It's D, where the difference is 3, right? The first difference is all 3, so it is constant. My next one, a quartic function. Now, a quartic function will have a constant in the 4th difference. So which option over here tells you that it's going to be a constant in the 4th difference? It's A. So we know that my quartic function answer is A. Next, we have quadratic functions. This one over here matches the criteria of a quadratic function, as the difference that is most applicable is the second difference, and that's what a quadratic function must have. My next one is a syntec function, and a syntec function has the 5th difference that's the most common. So we know that it is this one over here because the 5th difference must be constant. And the last one is a cubic function, and we know that a cubic function must have a constant 3rd difference. So we know, since it's the only option left, and also because our 3rd difference must be constant, that the answer to the cubic function one is E, the 3rd difference.
So next, I'll be talking about odd or even functions. Note that odd or even functions have nothing to do with its degree. You can tell if a function is odd or even using two ways. First of all, there's graphing, and second, you can check using algebra. So first, I'll be talking about how to determine if a function is even. If a function is even, you can check graphically, there should be symmetry through the y-axis. And also, if we were to check algebraically, the function would be even if f of x is equal to f and negative x. Let me show you an example. Okay. For the first example, f of x is equal to 3x squared plus 12. So in order to solve this, we have to see if f of x is equal to f and negative x, which means we have to sub in all of our x variable with a negative. So we're going to go f at negative x is equal to 3 negative x squared plus 4. When we solve this, we should see that it is equivalent to f of x, because we get 3x squared plus 12. And our therefore statement is going to be, therefore, since f of x is equal to f and negative x, the function is even. Now we're going to move on to it being graphically. If we look at a function, except let's say y is equal to 3x squared, we can see that this is a parabola. But if we look at the y-axis, we can see that it is the same on either side if we were to flip it. Because of this knowledge, we know that this function is going to be even. Determine if a function is odd. Graphically, we're going to see if there's rotational symmetry from the origin. That means if the function is rotated 180 degrees, the function should not change. To check algebraically, we're going to use the statement f of negative x is equal to negative f of x. Let me show you an example. Okay, so let's look at a function such as y is equal to 3x cubed. So I did a quick sketch of this, and if we were to see if this function was odd, we're just going to rotate it 180 degrees from the origin. So if we kind of visualize this, we're going to take this point, we're going to take these ones, we're going to rotate it 180 degrees. And if we do so, you will see that it is the exact same, which means that this function is odd. Next, we're going to look at this algebraically. So let's look at the equation f of x is equal to 5x cubed minus 8x. To see if this function is odd, we're going to do the exact same thing as if we were to do this to check if the function was even, except add an extra step. But first, we're going to check if the function is even. If we find out the function is not even, we're going to move on to the next step. So let's find out if the function is even. So we're going to go f of x is equal to f of negative x, and we're going to place all of our x values with a negative x instead. So we're going to f of negative x is equal to 5 negative x cubed minus 8 negative x. When we do this, we will see that our f of negative x is going to equal negative 5x cubed plus 8x. Now we're going to see if that is the same thing as our original function, which we see is not. So we're going to write a therefore statement, which is therefore f of x is not equal to f of negative x. And we're going to move on to our next step to see if the function is odd. So we're going to, with our new information of f of negative x, we're going to use a new therefore statement, which is f of negative x is going to equal negative f of x, which means our whole equation is going to be multiplied by a negative instead of just the one variable x. So we're going to go negative f of x is equal to negative, with the whole equation, 5x cubed minus 8x. When we multiply our signs, we're going to go negative 5x cubed plus 8x. And we can see that this equation is equivalent to our f of negative x equation. Therefore, since f of negative x is equal to negative f of x, it is odd. Note that a function could be considered an either if f of x does not equal to f of negative x, and also f of negative x does not equal negative f of x. So that means a function is neither, so it can be even or odd. Now let's look at an example that I made for you. So if we have the function f of x is equal to 60x cubed minus 47x, we're going to see if this function is even or odd. So in order to do this, we're going to first see if the function is even. So we're going to go f of x is equal to f at negative x. And we're going to solve by replacing all of our x variables with a negative x instead. So we're going to go f of negative x is equal to 60 bracket negative x cubed minus 47 negative x. And we're going to solve it, and we're going to get a final answer of negative 60 x cubed plus 47x. And this equation is not equivalent to our original f of x equation, so we know that this function is therefore not even. And now we're going to move into the next step to see if this function is odd. And we're going to go f at negative x is equal to negative f at x, meaning we're going Remember that we're going to multiply the whole equation by -1 instead of just the one variable. So we're going to go negative f of x is equal to negative, multiplying the whole equation by a negative, we're going to go 60x cubed minus 47x. And we're going to get an answer of negative 60x cubed is 47x. With this equation, we know that since this is equivalent to this, we know that the function is going to be odd.
What is AROC? AROC is the average rate of change. It is a measure of how one quantity changes quickly to another. So, for example, meters per second, dollars per hour, or moles per liter. In the sense of graphing, the average rate of change would be a slope of a secant line. And if you recall, a slope of a secant line is rise over run. The question for AROC is the buying price, P, of one stock of a company at any given time, T, in years can be represented by the function P of T is equal to negative 0.5 T cubed plus 3T squared plus 6T plus 2. Determine the average rate of change of the buying price from 1, year 0 to year 6, and 2, year 6 to year 9. So, the formula to solve this question is AROC is equal to the difference in y over the difference in x. So, y2 minus y1 over x2 minus x1. So, your y2 is year 6, and your y1 is year 0, because y6 is what you're ending off with, and year 0 is what you're starting with. So f of 6 minus f of 0 all over 6. And figure out what your value is for f of 6. In the end, you would get 38. The same thing you do with f of 0 to get your y1 value. And in the end, you would get 2. This is all over 6 minus 0, which is just 6. So you would have 36 So, part 2 asks you to find the average rate of change of the buying price from year 6 to year 9. So, the same thing as the last question. So, what is IROC? IROC is, first of all, the instantaneous rate of change. It is the rate of change at a specific point. On a graph, it is the slope of a tangent line instead of a secant. That is for AROC. So, as you can see on this, it is at one point, and it's the curve that is from the one point. So in AROC, you estimate the instantaneous rate of change using a very small interval surrounding the point, which means that if your point was 1, then you would do 1 and 1.001 as your two values. So the question for IROC, or the instantaneous rate of change, is During a penalty kick at a football game, the ball is kicked into the air in such a way that its height, h, in meters can be modeled by the function h of t is equal to negative 5.1 t squared plus 14t plus 0.7. Estimate the instantaneous rate of change of the height of the football after 2 seconds. The height of the ball after 2 seconds is approximately negative 6.5 meters per second. You write approximately because this answer is just an approximation, since you're using a value that is just close to the number and the actual number, which will give you a value that isn't exact but is very close to the value you want. And since it's an application question, you need to go further into the question and interpret what the answer means. So since our answer is negative 6.5 meters per second, this means that after 2 seconds, the height was decreasing.
Okay, so today we're going to be applying the knowledge that you learned previously. So the question is, Wonderland is opening a new ride and they have a prototype of the first drop. The equation of the first drop is f of x equals negative x squared plus 5x plus 4, where f is the height in meters and x is the distance it goes. The first question is A, where does the ride begin? B, when does the ride reach the ground? C, what is the ride's highest point? And D, graph the function and state the domain and range. So A, where does the ride begin? We're first going to answer this question by subbing in 0 for x, because we already know the x value will be 0. And since we already have one of the points, we can solve for the other point, which is going to be f. So over here, you can see that I subbed in 0 for x. So you're going to get negative 0 squared plus 5 times 0 plus 4. And we all know that 0 can't be squared, or it can't be a negative, and 5 times 0 is 0. So your ultimate answer will be 4. Therefore, the ride begins 4 meters above the ground. So for question B, when does the ride reach the ground? In order to figure this out, we're going to have to find the x-intercepts of the equation. So since the only way we can factor this equation out is by using the quadratic formula. So over here, you can see that I plugged all our values in for the quadratic formula. Negative 5 plus minus the square root of 5 squared minus 4 times negative 1 times 4 over 2 times negative 1. And when you simplify that out, you get negative 5 plus minus the square root of 41 over negative 2. Now you're going to get two possible answers because you're going to be adding and you're going to be subtracting. So when you add the equation, negative 5 plus the square root of 41 over negative 2, you're going to get negative 0.70. And when you subtract it, negative 5 minus the square root of 41 over negative 2, you're going to get 5.7. Now you're going to cross out this negative 0.70 because distance can't be negative, so the obvious answer will be 5.7. Therefore, the ride reaches the ground when the ride is 5.7 meters in. Okay, so for question C, what is the ride's highest point? We're gonna figure that out by adding the x-intercepts together and then dividing those by 2, and we're gonna plug in those numbers in our original equation. So over here you can see I made my own little equation where it's the x-intercept, the first x-intercept plus the second x-intercept over 2. I plug those points in, 5.7 plus negative 0.70 over 2, and I get the x value of 2.5. Now you're going to take that value and you're going to sub it in for f of x. So it's going to be f of 2.5 equals negative 2.5 squared plus 5 times 2.5 plus 4. And simplified out, that's going to be negative 6.25 plus 12.5 plus 4, which ultimately equals 10.25 meters. So therefore, the ride's highest point is 10.25 meters. Now for question D, graphing the function and stating the domain and range. So in our previous questions, we got all the information we needed to graph the function. So now all we literally have to do is just put it on our graph, plot the points. So we first figured out the y-intercept, which is 4. So over here you can see that the point is at 4. And then we figured out the x-intercept. So we have 5.7 over here, and then we have 0.7 right over here. And and we figured out our highest point, which was 10.25 over here. So all you have to do is just connect the lines and you're good. And now for domain and range. So to figure out the domain and range is actually quite easy. So first you're going to figure out the domain, and your domain is just the x-axis. And as you can see over here, the parabola gets bigger and bigger. So therefore, the domain would be x is a set of real numbers. Now for the range, that's all dependent on the y-axis. So over here you can see that the domain doesn't go any higher, or the parabola doesn't go any higher than 10.25. Therefore, your range would be y is such that y is less than 10.25 and y is a set of real numbers.
Alright, so first we're going to be talking about our basic understanding and knowledge of how we draw graphs and estimate the end behavior. So basics of end behavior. The end behavior describes the values of the function as x becomes very large or very small. It's determined by the leading coefficient and whether or not the function is even or odd. If a function has a positive coefficient and has an even degree, so let's take f of x equals x squared, for example, the end behavior will be 1, as x approaches positive infinity, f of x will approach positive infinity. And 2, as x approaches negative infinity, f of x will approach positive infinity. Whereas if we had a function with a positive coefficient and an odd degree, let's take f of x equals x to the cubed, for example, the end behavior will be, as x approaches positive infinity, f of x will approach positive infinity, and 2, as x approaches negative infinity, f of x will also approach negative infinity. So if we switched it around and had a negative coefficient with an even degree, so f of x equals negative x squared, for example, the end behavior will be 1, as x approaches positive infinity, f of x will approach negative infinity. And 2, as x approaches negative infinity, f of x will also approach negative infinity. A function with a negative coefficient that had an odd degree, f of x equals negative x to the cubed, for example, the end behavior will be 1, as x approaches positive infinity, f of x will approach negative infinity, and 2, as x approaches negative infinity, f of x will approach positive infinity. Important notes to remember about end behaviors is that an end behavior of odd functions are always different, and the end behavior of even functions are always the same. Next, we're going to be talking about the basics of orders. So an order helps determine the shape in which the graph shows. The highest power in a polynomial function is known as its order or polynomial degree. The order of a zero is determined by looking at the equation after it is factored. An exponent on a factor tells us the order of 0. The next thing that affects a graph are turning points. Turning points are points on a graph where the function changes direction. So a couple questions to test your understanding would be, what would happen to the sign of f of x near each zero of order 2? The answer would be, the sign stays the same and the factor will bounce off the x-axis. The next question is, what would happen on the graph at each zero of order 2? The answer is, a maximum or minimum will occur, which can be either local or absolute. So to begin, we're going to start by creating a function with a positive coefficient that is also quartic. So what does the 2 on each factor mean? Well, the 2 on this factor means that there will be a bounce on the x-axis at the 0 of positive 1. The 2 on this factor means that there will be a bounce off the x-axis at the 0 of negative 3. So now we need to find our y-intercept. So to find our y-intercept, we need to sub in 0 for x. So we're going to plot our y-intercept on our axes. Alright, so next we're going to plot our zeros. So when we take x minus 1 to the 2 and solve for the x, it will equal x equals 1. So our first x-intercept will be 1. So we're going to find that on our graph and plot it. When we take x plus 3 to the 2 and solve for x, we get x equals negative 3. How to connect them? So we know that this function is a quartic function. And it is also positive, which means its end behavior, if we can recall, will go up on both sides.
So now to connect them, we know that at x, that when x equals -3, there will be a bounce due to the order of 2. So we're going to connect it. We're going to go down like this, bounce off the x-axis, come back up, and now we need to connect it with our y-intercept, like this. There's our disgusting graph. So now we have our graph for our first quartic function. This graph, our first question is going to be 1. How many turning points are in this graph? Turning points is where the function changes direction. So 1, 2, 3. Number 2. How do the orders affect each graph? Well, we know that in this graph, the orders affect it because it bounces off of the x-axis. So we can write bounces that our domain is x is an element of all real numbers. And we know that our range is y must be greater than 0. X-intercept, or 0, at 2.